will go to the, they will, positive molecules, positive ions which are forming, they go to the, they get attracted through these lenses, which is negative here. Extraction plate is there. So this is how it is. And then matrix basically damages, matrix avoids the damages of sample molecules direct by interacting with atom beam. So basically it's like a small mediator. So matrix avoid the excessive damage to my sample molecules. That is second. Third is that as soon as these positive ions are extracted to my mass spectrometer, again matrix, since it's a liquid, it allows the fresh other molecules of my sample to come to the surface, so that thereby the surface is always renewed and more ions are formed. That is how the matrix role is there. So this we discussed, and then there is a small modification of this, which is we call it as a continuous flow fab is there, whereby there is atom gun is there, and then there is a sample is coming continuously here, whereby I can attach HPLC also to the FAB, but this is little less used because continuous flow fab is a modification, no doubt, can be used with the HPLC, but mainly FAB is used for the materials which cannot be chromatographed. So something which can be chromatographed, you may not use the matrix. Here there is a small modification in the normal this thing. Instead of putting the matrix here, the matrix is put inside the your eluent itself, so that as soon as it comes to this surface, there is a atom beam is there, then there is a formation of ions, and then there is extraction to the mass spectrometer. So now let us go to the next desorption techniques. Any question on this FAB?
No, sir.
Okay. No, sir. So the next desorption technique which we are going to study today, which will be the last technique of ionization. So we have studied EI, we have studied CI, we have studied thermospray, we have studied APCI, we have studied electrospray, we have studied FAB, and now this is the last ionization technique, which is called MALDI. MALDI is, as you can see on the screen, it is matrix assisted laser desorption ionization. So it's a very relatively simple technique. It's a simple in the sense, in principles it is simple, but the overall the equipment or the machine is a very costly affair. It's a very, as I said, it's a soft ionization method, can be used to volatilize large macromolecules with minimum fragmentation, use less multiple charging than ESI. So for proteins and other things, MALDI is very regularly used, or polymers, MALDI is used. Sample is co-deposited on the target place. This is very similar to FAB. There are only small modifications. Sample is co-deposited on the target plate with the matrix and allowed to dry. Many samples can be on the plate. Now, do you remember your chemistry practicals whereby there used to be a spot tile? Anybody remembers? See, when you do this qualitative organic analysis or qualitative inorganic analysis, you always take the CT, confirmatory test, at the end.
Yes,
You remember or no?
Yes, sir.
Yes. Where do you do the CT? Generally, you do CT in the spot tile. So there is a ceramic tile in which there are small compartments. You remember or no?
Yes, sir.
Yes. So exactly similar to that, this is a target plate. So there are small cavities are there, and in the small cavities, I can put number of samples. So these samples are mixed with the matrix, and then they are co-deposited on the target plate. So now and allowed to dry. So it's a dry sample, and there is no liquid wet material there, and many samples can be applied. Just like in a spot tile, let us suppose I got 16 cavities are there. I can have similar here to 16 samples can be put. Plate is then inserted into the instrument vacuum. So in the matrix, it's a process is very similar. MALDI sample is dissolved in matrix which absorbs the light. Now here only difference is that here the laser is used. Instead of atom beam or cesium ion beam, here I am using a short pulse laser of specific wavelength. So sample is dissolved in the matrix which absorbs light. From a short pulse of laser of specific wavelength, the sample gets ionized and extracted towards the mass analyzer. This can be coupled. MALDI is a very popular technique today for biomolecules and polymers. It cannot be coupled to the LC, but it can be coupled to the any kind of analyzer portion. That is, it can be coupled with the time of flight mass analyzer. It's a MALDI is basically, as I said, since it's a desorption technique, so it's mainly used for a very big molecules. So you can't use the analyzers which has got limited capacity of analysis. Like for example, if I say quadrupole machines are generally, now I am just going little ahead. Quadrupole is a mass analyzer. Quadrupole machines are generally used only for a smaller molecules, less than 1000 molecular weight, that is 1000 Dalton. Whereas if I have got a very high molecular weight of, let us suppose 1 million, 2 million, I cannot use quadrupole because quadrupole has no capacity of that kind of thing. So it has to be coupled with a mass analyzer which can analyze a very high molecular weight. So typical MALDI is coupled with time of flight mass analyzer, which is a mass analyzer is used. See, after this our desorption techniques get over. This today's stage, we are going to go to the mass analyzer. In the mass analyzer, we are going to study all these things. So time of flight mass analyzer is generally used in coupling with the MALDI. High mass range achievable. You can have very high mass. You can analyze. Calibrants may be external or included in the sample also. You may have some reproducibility issues. See, that is why again in MALDI also, you will not have the library. Library you can't have using the MALDI. Any of the soft ionization technique, you cannot have the libraries because soft ionization technique, slight changes in the conditions here and there, you will have some differences in the mass spectrum. Naturally, no libraries are existing here in case of a soft techniques. In a lab, if you have got a specific machine, you can generate your own library, but you may not be able to compare your mass spectrum with the other libraries because there are no libraries existing. Where are the libraries are there available? For EI. For electron impact ionization or electron ionization mode, there are libraries which are very standard libraries available. Like I told you in the beginning, NIST or Wiley is there. These are the two big libraries are there which are having lakhs and lakhs of compounds. Like if I am not wrong, Wiley must be having now 6-7 lakhs of compounds. So like all standard compounds have been, people have recorded a mass spectrum using EI with a quadrupole, and those have been recorded in the form of a library. Now here, as I said, there are reproducibility issues, so there are no libraries existing in this. So what is the basic funda? A target is there, which is mixed with the matrix. So it is irradiated by UV laser. Okay, it is a dried, it is not a liquid. Okay, it causes vaporization of the matrix. The matrix is assisting. So in case of fab, matrix is definitely helping, but there is no active role of a matrix. Still, here the matrix has a very active role. That is why it is called MALDI matrix assisted. So when it is target is irradiated by UV laser, now there are a variety of UV lasers I can use. Unlike the you have got atom beams in case of fab, here I am using UV lasers. So it causes vaporization of the matrix and supersonic expansion of the plum. Plum means that is the matrix basically. A dried sample is lodged into the gas phase as matrix is vaporized. UV energy absorbed by the matrix. Okay. First matrix is absorbing the UV energy, causes it to dissociate and typically transfers the proton to the sample molecule. So it's a very similar technique like APCI, whereby you have got but APCI is a spray technique, whereby my solvent is assisting. So that is why I call atmospheric pressure chemical ionization, where solvent is helping because solvent is first getting ionized and then it is ionizing. I am not mixing. APCI is entirely different technique, but phenomena or principles are very similar here, whereby matrix is assisting directly because UV energy which is from the laser is absorbed by the matrix first, causing it to dissociate, and then it typically transfers a proton to the sample molecule to form MH plus. So first it is matrix which is getting dissociated, transfer the proton to the sample molecules, and then the my compound of interest gets ionized. It is not that directly my compound of interest getting ionized with the help of UV laser. So now with the protonal target which can be accelerated into the analyzer for separation and detection. So once I have got MH plus, which is the positive ion I got, I can do the mass spectrum analysis. I can record the mass spectrum, and it has to be passed first to the analyzer, and I can record the mass spectrum. Unless I have got a positive ions, I will not be able to do the mass spectrometry, because requirement of an ion is a basic fundamental of a mass spectrometry. If something cannot be ionized, then I cannot do the mass spectrometry. Just like in a infrared, your compound must absorb the infrared radiation, then only you can record the infrared spectrum. Here also, if the sample is not getting ionized, if it remains neutral only, it cannot be studied by mass spectrometry. So once you get here, with the help of matrix, you are getting MH plus ion, then those materials can be analyzed using a mass spectrometer. So this MH plus which is formed, MH plus means one proton it has transferred, that is why it is called MH plus or M plus 1. Now this will go to the analyzer portion and it will get analyzed. So this is the diagram you can see. So whereby there is a the plate is there, the matrix is shown by the small sphere which is the empty sphere, and this is the product. So you can see large quantity of matrix is there. There are my compound of interest, which is all, this is shown as vertical, you can show it as horizontal also. So this is the plate which I am just moving my cursor. This plate can have 16 cavities, it can have 24 cavities, it can have 32 cavities, whatever is there. So this is the arrow which is showing the laser beam. So the laser beam is there, then the matrix is there, it causes supersonic expansion of first matrix gets, it absorbs the energy, and then there is supersonic expansion of the plum or the matrix along with my compound of interest. So then there is a flight, in the sense the matrix takes the compound of interest into the space, whereby air, it is evacuated space basically, not air, there is no air here, so it's a evacuated space. So here there is a, this matrix is subsequently going to transfer its energy of the proton to my compound of interest, and then you can see there is a desolvation, there is a proton transfer, and this is the place whereby I get the positive ions, and matrix is there which has got transferred, so naturally there will be negative. So that I don't want at all, I am only interested in positive ions. So this is how it works. Any question on this?
No, sir.
Okay. Which matrix that we will see subsequently? You can have a variety of matrix depending upon the compound of interest. So again, a little this thing, sample is mixed with the matrix and dried on a plate. Laser flash ionizes the matrix molecules. Sample molecules are ionized by the proton transfer, and you get MH plus. So this is the plate or the grid whereby my MH plus will be extracted, and it will, this portion will be the my mass analyzer portion. This is my sample plate. So this is a typical Manley-Top mass spectrometer. You can see the principle is very simple. It is only I have to take the sample, I have to mix it with my matrix, I have to dry it, I have to deposit it, I have to first deposit it on the plate, then I have to dry it, and then I have to bombard it with a UV laser. When I am bombarding with a UV laser, my UV laser radiation will be absorbed by matrix. Then there is a supersonic expansion of the matrix. It will take the sample molecules into the evacuated space, whereby there is a transfer of a proton from matrix molecule to my compound of interest. There is a formation of MH plus, and then this MH plus will be accelerated to my mass analyzer portion, and mass analyzer portion will be analyzing my masses which are coming from my ionization source, and then I will get a mass spectrum. So this is a typical Bruker Manley-Top. You can see it's autoflex, it is called. It is a very big machine, and it's a very sophisticated machine. It costs crores and crores of rupees. Maybe I think in not less than 3-4 crores easily. So Maldi is a very costly technique, and naturally it is not used for small molecules. If I have to analyze by benzene, toluene, xylene, Maldi is not for that. Maldi is only for those molecules which are very high molecular weight, like all proteins, peptides, some of the polymers, all those things can be analyzed using the Maldi. So this is MALDI is a source and connected with the time of flight mass analyzer. Now this TOF, time of flight, these are typical acronyms you will find. So you will find MALDI TOF or QTOF or this kind of acronyms. So as we study further, you will know the acronyms also. Short forms, all of them. So it's easy to use, walk-up use after the training, highly automated and can be used for imaging. You can use the imaging technique also for MALDI, using MALDI. Anybody knows the imaging technique using infrared? Have you studied the imaging using infrared? See, there used to be an infrared microscopy. Like if you have studied infrared, have you studied infrared first?
Yes, sir.
Okay. So you must have studied infrared whereby sample is mixed with a KBR, right? And you have to make a small disc and then subsequently it has to be put into the chamber and then infrared light will be put on that and then you are going to record the infrared spectrum. This is how it works. Similarly, if I have to do some that say let us suppose some tissue analysis, I can, in case of infrared microscopy, FTIR microscopy, I can take the sample and I can choose the smallest possible portion and instead of going in the transmission mode, I can go into the reflection mode. And if I do reflectance spectroscopy using infrared, then and I can use the microscopy I use, it's a typical infrared microscopy whereby I can smallest possible spot. Let us suppose I do some coatings. I do say let us suppose there is a some very fine coating is done on say let us suppose I am saying platinum coating is done on something. I want to analyze. Let us suppose that or maybe some other organic pigment coating is done on some small surface. I want to analyze if this coating is uniform. I am not able to take out a sample. I have to do the non-destructive testing only. So then I may do that sample. I may take that sample and I may use the infrared microscopy and I may take the if it is organic compound, I am recording those organic pigment infrared and I am basically taking the infrared spectrum spot by spot. So that is how the imaging it is called. So similarly, just like you do FTR microscopy, here also I can take the surface and I can do the imaging, like a tissue sample is there and then I can do the spots by spot analysis. I have to use the matrix no doubt here also and then it is mixed with the matrix. Instead of destroying that, a spot by spot analysis can be carried out. So it is called MALDI using imaging technique. So it's a imaging of a tissue samples. Concentrations are very small, like something like 10 picomoles. Very small concentrations can be used. I do not need a very large quantity of material. The ratio of matrix generally 10 part of matrix and 1 part of sample. So 10 is to 1, that is there. So several methods of target preparation, multiple layer, co-mix, there are variety of this thing. So I have to use a very small quantity. I have to take 10 parts of matrix and 1 part of sample. Various matrix are used, that is there is alpha cyano 4 hydroxycinnamic acid used for typically for peptides. Then 3,5-dimethoxy 4 hydroxycinnamic acid which is typically again used for proteins. You will not find in the list applications like a small molecules, like let us suppose I want to analyze say sugar, simple materials like xylene or maybe some of the pesticides. You will not find in the list. Why it is not in the list? Why it is not in this list applications? Because these are very simple molecules. If something which is less than 1000 molecular weight, they are very simple molecules. You do not need MALDI for that. You cannot use hammer for just killing a fly. So basically a very small molecules are there which are less than 1000 Dalton or 10,000 molecular weight. There are many other simpler and very cost effective or cheaper techniques. You do not need MALDI for that. MALDI is required only for those molecules which are very high molecular weight. That is one, available in a very small quantities. So it is typically used for peptides, proteins. So there is a 3,5, as I said, 2,5-dihydroxybenzoic acid DHB is used for peptides, again proteins, polymers, sugars. 3-hydroxypicolinic acid is used oligonucleotides. Then anthraline is used for the polymers. Variety of matrix are there. Even you can, if you start using bioanalytical research afterwards, after your MSc and PhD is over, you can have variety. You can also invent some matrix whereby you may use that matrix for your molecules. So it has to be always it's an experimental aspect. So you can have variety of more and more list can be there. It is not like a fixed. Only these matrices have to be used. These have been already used by the people, scientists, and they are very successful. But one can always try some other things also. Maldi-Toff, or I am saying now this is a general characteristics of a Maldi-Toff, matrix assisted laser desorption ionization time of flight. Okay, so that is Maldi-Toff. Generally results in a broader peak than ESI. Low Maldi-Toff less than 20 can use the reflectrons, get high resolution. Now when we study the TOF, I will tell you about the reflectron. High molecular weight requires linear mode, low resolution, that is more than say 5 lakh daltons. Typically, you get singly charged, not multiply charge species. Analysis is very rapid. Therefore, it is often used as in high throughput analysis screening applications. Like let us suppose I want to, as I said, I was talking about some tissue culture analysis. I want to record say 500 spectrums at a time. So I can do using the MALDI, or maybe I may use the plates, number of plates. I may go on depositing the samples, and it's a very high throughput analysis I can do. There are variety of modifications of Maldives possible, and people have given different names on that. Applications are many. Any questions on theoretical aspects what we have studied today about Maldives?
No, sir.
Okay. So it's a simple technique. As I said, I will just recap once again. I have to take a matrix. Now which matrix? I have given you already the list. This is to be, matrix is to be mixed with my sample of interest. MALDI is to be used only for a very high molecular weight compounds, not for low molecular weight. For low molecular weight compound, there are many cheaper techniques, very cheap techniques. EI is the best technique for low molecular weight compound. So when I am going to use MALDI, it is only for those compounds which cannot be analyzed by normal techniques. By normal techniques like my EI, CI, electrospray, all those things. Then only I am going to use the MALDI. I am not going to use MALDI just for the sake of fun. So because it's a very costly technique, as I said. So typically used for proteomics. So as I was telling you, just I am recapping. I am taking the matrix, mixing with my sample of interest. Then I am putting it on my plate, and I am going to dry it. Subsequently, after the drying, that sample plate I am going to bombard with a UV laser. The UV laser will interact with my matrix of which I am using, and it will absorb, my matrix will absorb the energy. It will have this, there will be supersonic expansion of my matrix, that is we typically call supersonic expansion of the plum of the matrix. And because of the supersonic expansion of the matrix or the plum, it will take the sample molecules into the vacuum space, basically vacuum space it will take, and then there will be transfer of energy, that is transfer of a proton basically from my matrix to my compound of interest. So I will get my compound of interest will become MH plus, which is the ion, positive ion I got. As soon as it is proton antidote forms the positive ions, then it will be extracted using the mass analyzer portion. It will get attracted to my basically the lenses, the negative lenses, and then subsequently the collimation and other things will happen, and it will go to the mass analyzer portion. It will get analyzed. So this is how the MALDI works. So it's used for advanced proteomics and other areas of biotechnology, protein peptide analysis or molecular determinations, protein identification, profiling in digest database. So I used a lot in drug discovery also. Particularly, if I am seeing some effects on my biological molecules, what happens? Then I can use MALDI. Then protein peptide analysis. It is not used for the drugs analysis as such, which are smaller molecular weight. The effect of the drugs on basically the body or the other things, like some of the other biomolecules, what happens to those molecules? So that is how it's studied. So protein peptide analysis or molecular determination, protein identification, profiling, protein post-translational modification, protein structure characterization, MALDI imaging, oligonucleotide analysis. So purely a bioanalytical application or biotechnological application. It is not used for simple molecules. It's a very automated high throughput analysis, screening of biological sample, pharmacokinetics, separation and identification using complex mixtures. Virus analysis it can be used. MALDI, cell imaging, tissue imaging. It's a very advanced technique and used only for really those materials which cannot be analyzed by simple techniques. So this is a typical MALDI. You can see the MALDI spectra of a monoclonal antibody. So the currently which all the virus research is going on, you can see the antibody studies and other things are being done by so many pharma companies. Their MALDI is used a lot. People have been using MALDI for that, for all the research. So you can see the, like for example, there are 3 protons here, they are transferred, here 2 protons, there is a 1 proton. So depending upon that, my m by z will change because it becomes 3 proton transfer, I will get 3 plus, 2 proton transfer, I will get 2 plus, and here I will get 1 plus. So the same molecule may be there, but because of the multiply charge, I may get the 3 peaks, like that it will be there. That can be same molecule, it can be different molecules having the different weights charge also, that also is possible. So this is a typical MALDI. So the same thing which I have shown you. So now we have studied MALDI. The features of the MALDI also we have studied. It's a very useful technique for biotechnological applications, and it is very used a lot only for advanced research, not used for simple pesticide or other agrochemicals or simple molecules research. MALDI is not a technique for that. It is used for very advanced biotechnological applications. So we have seen the brief fundamentals and application parts and how it is used. Any questions on this?
No, sir.
Okay. If there are no questions, what we'll do, we'll take 5 minutes break. Just now it is 11:03, so we'll again continue at 11:08. Okay. And then the last ionization we are going to discuss is basically ICP. Okay. After that, our ionization techniques will be over. And today we'll stop after the ICP. And from next time, we'll start with the mass analyzers. Okay. So let us have 5 minutes break.
Yes.
Let us continue. Okay. Everybody is there or no?
Yes, sir.
Okay. So we'll continue now. So now the last ionization source we are going to study is the ICP, inductively coupled plasma. You heard about ICP? Anybody has heard about ICP?
Yes, only heard the name.
No, sir.
What is that? Where it ICP is used? ICP is a very popular technique, okay, for inorganic analysis. It is not for organic analysis. It is typically used for the inorganic analysis. Now, ICP OES or inductively coupled plasma optical emission spectroscopy is a very popular technique which is used in a inorganic analysis. Okay. So, in inorganic analysis, particularly when I am doing like you must have heard about the atomic absorption. You have heard about atomic absorption or no?
Yes, sir.
Okay. So when it is the atomic absorption, it's the absorption spectroscopy. Okay. Where it is the ICP OES when I call ICP inductively coupled plasma optical emission spectroscopy. It's a emission spectroscopy. Okay. Now today we are going to discuss ICP as not as a OES technique. I am going to discuss today ICP as a source or the ionization source. Now the question must come in your mind, if let us suppose I have got an inorganic molecule. We discussed a lot about organic analysis. If let us suppose I have got inorganic molecules, then how do I study? So because all the other techniques what we discuss, they can't be used for inorganic materials. Like let us suppose I want to do, let us suppose any other atoms like say sodium, potassium, any other thing I want to do. These things cannot be analyzed by my normal mass spectrometry. So it has to be, because all the other things what we discussed, EI, CI, thermospray, it is all for organic mass spectrometry, not for inorganic. So this is the ICP is the technique which we are going to discuss, which is a source. Okay, it is a source for analyzing inorganic samples. So I will share the screen. Can you see the screen?
Yes, sir.
Okay. So ICP is a source which was originally developed for atomic emission spectroscopy. As I discussed, ICP OES was the first technique which was developed for emission only. So just like your atomic absorption spectroscopy, in ICP what you do? You basically take the inorganic molecule or inorganic atoms to their higher state. When they are taken to the higher state, then they come down to the ground state by emitting the characteristic radiation. That is emission spectra you see. So here ICP is used as a source for inorganic compound. So ICP, then you call, instead of ICP OES, which is the emission spectroscopy technique, here I call ICP MS, because here I am using ICP as a source, not for emission spectroscopy. It is basically for mass spectrometry I am using. So as it's already given in the slide, ICP MS. So ICP, you must always remember ICP OES when I talk, it is a normal spectroscopic technique, which is ICP OES, emission spectroscopic technique. When I call ICP MS, then ICP is used as an ion source. It is not like a ICP OES. So ICP MS here is because see, ICP is only used as a source. MS has to be there. That is the mass analyzer portion will remain. Just like we studied thermospray, atmospheric pressure, chemical ionization, electrospray, all those things, that they were all ionization sources. Similarly here, ICP is a source. Clear? Now, ICP-MS is capable of trace multi-element analysis. See, I can do very traces in parts per billion, even than that also, parts per quadrillion. That kind of analysis can be done using ICP-MS. It can detect all the elements except fluorine, neon and helium. Ionization efficiency is greater than 90% for, again it depends. Although ICP is the source, it should be able to ionize my molecule of or compound of interest. Basically here I am saying inorganic elements. If it cannot ionize, then I cannot use ICP. Okay. So here it can detect all the elements except fluorine, neon and helium. These somehow these cannot be ionized using ICP also. So there the ionization efficiencies are very poor, not so good, and so ionization efficiency is good for 54 elements. Overall, as such, you can see ICP can be used for 50 to 60, out of which 54 elements can be very successfully because the ionization efficiency is greater than 90%. So you can easily get a good signal. So how does it work? You can see here there is a diagram, and then there is a, you can see there are three concentric tubes are there. There is a 1, 2, 3. So there are three concentric quartz tubes are there. Argon flows through each of that at atmospheric pressure. Every tube there is argon flows, and it is cooled induction coil surrounds. There is an induction coil. So there is a induction coil is surrounding the top largest tube, powered by the RF generator. Okay. So there is a radio frequency waves are there. There are radio frequency waves are there. These RF will be initial Tesla spark will ionize the flowing argon. RF field accelerates. So the initial spark is there which ionizes the argon. There is argon continuously flowing. This argon is then RF field is there which is surrounding the top largest tube. This is powered by RF generator. This RF field accelerates these ions. Once there is a spark is there, the ionization happens of the flowing argon. That is further accelerated again and again, leading to the collisions and more ions. So equilibrium between ionization and recombination. So because of this, you will find this is a can you see this like a flame type material? This is the basically the argon torch is there, whereby you can see the ICP. This is inductively coupled source. So this is like I see this, and then I can see the temperature of the plasma. This is typically a plasma. Plasma, you must be remembering, the plasma is a state of matter. There is the first is a solid, then the liquid, then there is a gas, and after the gas there is a plasma. Here the state of the matter is a plasma. Okay, this plasma reaches this plasma of argon. Okay, this is not a plasma of any other material. This is a plasma of argon. So the plasma reaches the temperature of 10,000 degree Kelvin, very high temperature. You can imagine 10,000 degree Kelvin is a very high temperature. And if I put any material, inorganic material I am talking about, see, no organic matter can be analyzed using this. Can you analyze tissue using this? Because 10,000 degree Kelvin, which material will stand? All my tissue which are made up of basically the carbon, hydrogen, oxygen, they will all get converted to carbon dioxide, water vapor. Okay, so I can't just study anything. So this can be used only for studying the inorganic molecules. Okay, plasma reaches the 10,000 degree Kelvin. So is this fundamental clear? Sample, vapor or droplet carried into plasma through central tube. So there is a, just like atomic absorption spectroscopy, there is a sample solution is there. There is a peristatic pump is there. There is a nebulizer is there. This nebulizer will take, so the carried into the plasma, high temperature, at high temperature dissolve it. Whatever the sample is there, it will dissolve it. That is removal of solvent. Then vaporization. If it is water, it will vaporize the water vapor. It will only keep my sample of interest into that. That is the inorganic atoms. Vaporizes. Then it will atomize and ionize. Since the temperature is very high, each and every atom which is there will get ionized. So it is close to 100%. For the atmospheric pressure ionization sources, transfer to MS require differentially pump interface. So basically the samples, there is a plasma here, there is RF generator, there is a continuous flow of argon is there. The argon, as I have shown you here, the cooled induction coil is there which surrounds the top largest tubes. There is initial Tesla spark is there which ionizes the flowing argon. As the first argon is ionized, the RF field will further accelerate our ions because there it is radio frequency waves are there. This field is there which will accelerate. As it accelerates, it will lead to multiple collisions to form more and more ions. As there is a more and more ion formation, there will be equilibrium will be established. There will be ionization. Some ions may collapse to form they may recombine also. There will be equilibrium between ionization and recombination. That is how the argon plasma will be generated. It looks like a flame, similarly. And the temperature of this is very high, 10,000 degree kelvins. Why this then 10,000 degree kelvins? No inorganic molecule can remain really in their original ground state. They will all get ionized. Okay. And when they get all ionized, then as I said, there will be a almost efficiency of 100%. So the sample, just like an atomic absorption spectroscopy, the sample solution is there, there is a pump is there is a nebulizer is there which will be spraying. As the sample is sprayed into the ICP, that is inductively coupled plasma, there is a plasma here. Then the sample will desolvate, that is if at all it contains water or it contains acid or whatever it may contain, it will all remove all the solvent. It will vaporize completely, it will get atomized completely and it will get ionized subsequently. At 10,000 degree Kelvin plus temperature, no material or inorganic of type can remain as such. It will get ionized guaranteed. So the efficiency is close to 100%. As soon as the ions are formed, then this is the ion extraction chamber is there. There will be lenses. Those lenses, the positive ions will be extracted to the lenses because these are negative lenses. They will attract my positive ions. They will go through this, and then there is the collimated ion beam will be there. It will go to the analyzer portion. Which analyzer? That we are going to discuss subsequently one by one. Okay. So this is a very simple technique, but very effective technique for all the inorganic. So ICP-MS, since the efficiency of ionization is 100% almost, because the temperature is very high, so you can detect the inorganic materials at a very low content. You can easily detect to parts per billion, some cases parts per quadrillion also, ppq. ppb is absolutely the very easy stuff. So you may always want to detect some of the inorganics also. Like if let us suppose I want to detect, have got some metal based, say let us suppose drugs are there, and which I want to track those metal based drugs in my body fluids or maybe at some other tissues, how they are penetrating or what is happening to those. I can study using ICP because I want to determine only those metal stuff. ICP is not a technique for organic biomolecules, okay? Because the 10,000 degree Kelvin, nothing can withstand, okay? All those organic biomolecules, if it there, if I spray proteins, peptides, they will all get converted into the carbon dioxide and water vapor. Nothing will remain. So I can't use this technique for the organic biomolecules. It has to be used only for where there is a inorganic some of the species which I want to track and I want to determine that at a very low content. Again, if let us suppose my substances at a very high concentration in terms of say let us suppose percentage or ppm, then ICP-MS is not a technique because there are many cheap sources available or cheap techniques available. Like I may use a normal flame photometry also for some techniques for alkali metals typically, or I may use maybe atomic absorption I can use easily, or I may use ICP-OES. I need not use ICP-MS. ICP-MS is a very costly technique again because the mass spectrometer involved, and ICP is a source anyway can be used along with optical emission also. So it's not a technique for a simple inorganic species which are in a larger quantity. They are only to be used where very specific things, and I want to determine in very low content. There only ICP-MS to be utilized because then it's such a costly technique. I can't just afford to use it for a simple materials. It has to be used only for the special cases where normal techniques they fail. So and this is a very simple, as I said, can determine to ppm, ppb, ppq, but it is not for ppm analysis. It can be used for ppb and ppq, that kind of analysis. Very simple technique. Just we will again recap once again. There are three concentric quartz tubes are there, Argon continuously flows through each of the at atmospheric pressure. There you can see there are 3 concentrated tubes here. This is typically the where the flame is or the ICP is get generated. It is called a torch. Okay. Then there is a cooled induction coil is there. You can see this is the cooled induction coil is there. Surround the top of the largest tubes powered by RF generator. There is a radio frequency generator is there. Initial Tesla spark ionizes the flowing argon. There is a continuous flow is there of the argon. There is an initial spark which ionizes the flowing argon. As there is a ionization of the argon, then small ions are formed because of argon. Then there is a radio frequency there and comes into picture. This radio frequency field accelerates these argon ions. As it accelerates, there will be leading to the collisions and formation of more and more ions. So this continuously multiplies, more and more ions forms. Subsequently, there will be ionization and then there will be formation of there will be recombination also. So there will be equilibrium will be established in ionization and recombination. As this equilibrium reaches, there will be steady plasma formation will be there. That is because of the argon, whereby the temperature will be 10,000 degree Kelvin. The temperature of 10,000 degree Kelvin is a very high temperature, and no material of whatsoever can remain as such in a normal state. It has to get ionized. Again, as I said, this is not a technique for organic molecules. This is a technique for metallic substances. I can use organometallic substances. I can use typically. Let us suppose I want to study hemoglobin, which has got Fe. I can study using ICP-MS, but I will not be able to see the pure protein molecules if they do not contain any other metal ions. This is not to be studied using ICP. So the technique, as I said, is very simple. Just like atomic absorption, there is a sample solution is there, which is pumped through the peristatic pump is there. There is a nebulizer. This nebulizer will form as fine droplets. As the temperature of the plasma, this is the plasma, it is getting, my sample is getting spread into that. A high temperature dissolve it. There will be removal of the solvent, whatever I am using. Then there is vaporization. Okay. Then there is atomization. And then there is ionization. Because of all this high temperature of 10,000 degree Kelvin, the efficiency is close to 100%. There is no loss at all, absolutely. So naturally, when there is no loss, my sensitivity of my ICP is very, very high. So I can easily determine parts per billion, parts per quadrillion to be used only for inorganic molecules. Typically used for 54 elements in the periodic table, I can use ICP-MS. Very simple technique. Any questions on this? Any questions?
No, sir.
Is it clear? Is ICP-MS is clear?
Yes, sir.
Okay. So now which MS or which mass analyzer that we are going to study separately. So we discuss, basically we started with the mass spectrometry basic fundamentals. We discussed about the why high vacuum is required in the mass spectrometer. We discussed about the pumps which are typically used for generating the high vacuum. Then we discussed about the sources which are typically used for forming the ions. So we studied with EI, we studied CI, then we studied the other spray techniques also, that is thermospray we studied electrospray, we studied the atmospheric pressure chemical ionization, then we studied the desorption techniques, that is we studied the fast atom bombardment we studied the MALDI, that is matrix associated laser desorption ionization, and we studied ICP. ICP is the only source which is used typically for the ionization of the molecules which are inorganic in nature. Okay, so if you just see the table, if I got EI, PI, thermospray, FAB, APCI, ESI, MALDI, this is what we studied all of them. Okay, so you can see non-polar and some polar organic. Typical technique in case of EI separation, which I am using is GC. For CI, typically I am using again GC. For thermospray, then it comes to LC. The inlet portion comes as it differs. The FAB, again I can use the continuous flow FAB LC. I can use CE also, that is capillary electrophoresis. In APCI, I can use LC, ESI, LC. Again, capillary electrophoresis can be used. In MALDI, again, some very rare cases LC are used, but generally it is used as a standalone technique. Some places people have used CE also. Typically use both these. MALDI and FAB are used for very high molecular weight compounds which are not easily chromatographiable. So the typical ion formation you can have in EI M plus. Subsequently, you will have always proton transfer. That is M plus 1 or M minus 1 or M plus 1 or M plus multiple. Like that, there will be like ESI, you have got M plus multiple protons. Or here also I can have the M plus proton. That is M plus 1. So like that, these are the typical ionizations happening in variety of ionizations. Now why we have to use variety of ionizations? Because every molecule has a different characteristics, every type of the metal has a different characteristic, and naturally one single ionization source is not enough. So variety of metals, variety of ionization sources, that's the basic fundamental. So people have got Nobel Prizes as I discussed in the beginning itself, and mass spectrometry is a very well known and studied, and today also a lot of research is being done in mass spectrometry. So next time what we are going to study is mass analyzers. So we are going to study typically the time of flight analyzer we will study. First we will start with the quadrupole, then we will study ion trap, then we will study magnetic sector, and then we will study time of flight. So these are the four mass analyzers which I have shown in the red we are going to study from the next time. So with that, once we cover mass analyzer, and then subsequently we are going to study other detectors also. That will be not a small, this thing. Maybe in the next two sessions we are going to complete our basic mass spectrometry. Any questions in today's discussion what we discussed? Any questions?
Understood.
Understood. Very well. But my request to all of you is that please revise, because many of you are not from chemistry background, and so and you have no options in when it comes to the mass spectrometry. Bioanalytical chemists have no option. Mass spectrometry is like a bread and butter, and it must be, you must not only understand, you must get an expertise, that is requirement. And many of you are going to be doing PhD. You will have the mass spectrometry is a very essential technique everywhere. Without mass spectrometry, no bioanalytical lab will work really. Okay. So if there are no questions, we'll stop here, and then we'll meet again on next Saturday. Okay. Bye bye.
So can you share the presentation?
What is that?
Can you please share the presentation as we have Maldi and ICT in the
I will share. Share means right now?
so if possible today.
No, no, how means you need to give me email. Email I will need na, because I can't send like this as here.
So can share it
Send me,
directly.
anybody can, you just send me your, my number is 98205
So 1 minute.
98205 98205 23794 23794. Have you written down?
Yes, sir.
What is the number?
98205 two three
Mhm.
seven four.
794, right? So what you do, this is my WhatsApp number. So anybody can send your email ID on my WhatsApp. So I will forward some of the required slides to you.
Okay, sir.
Okay?
Yes, sir.
Okay, bye. All the best. And you must revise.
Thank you, sir. Bye.
Bye bye.